This
we
is a
gonna
good
go
answer.
over 13 and 14?
So that was like that Michael Orr movie, you know, where he like puts his arm out and stops. They're like going 50. It's just like,
Oh, that's good.
Let me look at what I
Because
got.
he's like 80 pounds of metal.
I got 1.99 times 10 to the fourth.
Are you talking about the
3
black
point-
side?
Okay,
sounds like one.
I don't
all
know.
right. Now, let's talk about question number 13. Okay? So, there was a time that might be known as BW, which stands for before Walmart, okay? Civilization did exist before Walmart, okay? Worse yet, for your generation, there will be a time referred to as BC, which is before cell phones, okay? Yes, that existed too. We'll talk more about those dark ages later. So, it used to be, number one, there wasn't Walmart. Number two, the whole idea of like child safety seats did not exist, okay? Safety helmets when you rode a bike did not exist, okay? So, like I remember, I grew up around Cheney, and I remember riding into town with Dad in his truck, and I was shorter then, and I just stood up in the seat beside Dad, okay? That's how everybody did it. So, you know, I was standing up in the seats, you know, Dad was driving, I'm standing there. And when Dad would hit the brakes, if he had to hit the brakes, he'd put his arm out and stop me. Sometimes he pushed me forward, but for the most part, Dad would just try and stop me. And so that's what everybody did, because there weren't child restraint seats. So you could always tell, like, a mom who had driven around with a lot of cars, whenever and it was just an instinctive thing, whenever they would hit the brakes, whether the child was there or not, the mom would sometimes just instinctively put her arm out.
My mom still does that. Like,
Yes.
She still,
Yeah.
and like sometimes I'll be like, what are you doing? Like, you just stopped at a stoplight.
It's just instinct.
Still, she does
I
that
do it
every
just
single
because
time.
I'm that bad of a driver that I.
You think it's going to help?
Would that help you?
Okay, so what happened is that the physicists of the world kind of said, look, let's look at the math here. So let's look at what I've got on 13. You had a 10 meter per second crash, not all that fast. Okay, world-class sprinters can run this fast. This isn't like you're driving at the Indianapolis Speedway. This is 10 meters per second. It's not all that fast. So you're going to stop in 0.35 meters about like yet. Okay? So it isn't like instantaneously. There's some distance involved here. So the kid has a mass of what, 20 kilograms, 40 pounds, roughly. Okay? So what we want to look at is if you want to stop Kimmy by just using one arm, what I want to figure out, that's the equivalent of trying to lift how many kilograms and how many pounds. So on 13A, because the 13A is wrong, everything else is going to be wrong, okay? So 13A should be around like 0.07, okay? Ish, all right? Now, what you can't do is distance over time equals velocity because of the fact that Timmy is slowing down, okay? So you can do the triangle on a velocity time graph, and you can use 1/2 v plus v naught times time, same thing, okay? So what you should see is that your answer to C, if you got that right, should be around 300 kilograms, okay?
To see? Is that
Yeah.
like a ish?
Ish. I said around 300. So that's around 300. So 2.2 pounds is like 1 kilogram, so that's like 600 and some odd pounds. So in other words, so you trying to stop a kid in that amount of time, in that distance, is equivalent to you taking one arm and lifting about 600, more than 600 pounds. And the physicists are going, Mom, you know, we appreciate you're superhuman, all this good stuff. You're not going to stop your kid from flying through the windshield. It's just not going to happen. And this is a relatively low-speed collision. This isn't a high-speed collision. So they basically said, we got to do something else, and that's really kind of what led to the idea of child restraint seats and everything else, because otherwise you just kind of had carnage. It was a bad deal.
About 14.
What about 14?
Yeah, can we go over that?
Can you give us a
What
ballpark?
was the ish?
Yeah, just give us an ish.
Yeah, can we get an ish on that?
An ish on 14 is around 9-ish.
Like round?
Okay? So, look, there's two ways that you can approach number 14. Okay? It says, what is the momentum of 1.2 kilogram mass dropped from a height? So there's two ways that you can approach this. First off, is the momentum going to change? Yeah. Okay? So change in momentum is mass times v minus v naught. So one option is that you know the initial velocity, you use that equation and you find the final velocity, multiply it by the mass as your change in momentum. That's an option. Okay? The other thing that you can look at is that you can use force times time. Well, when you let go of it, what's the force acting on the ball? Gravity. So you can find mg and say, okay, there's your force, and then you can use t equals the square root of 2x over g to find the time. So multiply the weight of the object by the time, and you can find the change in momentum that way. Because if you look at this on a force time graph, okay, the force is your gravitational pull acting over however long it's in the air. You can do it that way. So you can either find the final velocity and multiply it by the mass, or find the time that it's in the air and multiply it by the weight of the ball. Either way, there you go. Some of your answers on this assignment should be negative, okay? Not a lot of them, but you should have some negative values. And if you don't have any negative values, just don't randomly go through and chuck negative signs on them. That would be bad. Make sure on number 8 you have a force time graph, and there's two distinct parts to that graph. Okay? So make sure that I can clearly say, oh, here's my force, here's my time, and here are the corresponding values. So make sure that that is very clearly laid out. Anything else? Once, twice? So when you look at science, over the years, centuries actually, we've come up with certain great conservation laws that are kind of the bedrock of all of science. So if you've been through Chem 1, which I'm guessing most of you have, you learned about the law of conservation of mass. That's what allows us to balance chemical equations. So the law of conservation of mass says that, Ms. Treadway? Bingo. Mass cannot be created or destroyed. However much mass you have as a reactant has to equal the same mass as the products. Okay? There you go. And that sounds pretty intuitively simple, but it was actually kind of debated for a while because a lot of times it's so hard to measure like changes in mass on a chemical reaction, especially if gases are involved. So they established that. And then later on we said, because of Einstein's equation of E equals mc squared, mass and energy actually became intertwined, because you can take energy and get mass out of it, or you can take mass and get energy out of it. So this became equivalent, because if you look at what happened with the Big Bang, it started off as pure energy. That energy basically then got changed into mass. Then in nuclear reactors, for example, we take mass and we convert that back into energy, which is why we're getting energy from the sun, because of the fact that all this hydrogen is combining into helium. There's a slight drop in mass. That mass is converted into energy. We get sunlight. Okay. So what we're going to worry about eventually are two things: linear momentum and angular momentum. Okay? They're both conserved. Now, so basically, if you look at what Treadway said about mass, it said, okay, mass cannot be created or destroyed. The same thing is true of linear and angular momentum. So however much momentum you have at the beginning has to equal all of the momentum when you get done. Okay? So basically, if you understand the concept of conservation of mass, it's the exact same idea as the conservation of momentum. Now, you can also have the conservation of charge, okay, which is why when you ever balance net ionic equations in Chem 1 or Chem 2 or AP Chemistry, the sum of all the charges on one side have to equal the sum of all the charges on the other. So all four of these have the exact same format. It says, okay, whatever you have at the beginning has to equal the same amount that you end up with at the end. Now, so what we're going to focus on is this idea of linear momentum. We'll deal with angular momentum later. So here's the basic idea with linear momentum. And what you'll see is that linear momentum problems aren't horribly difficult. You make them difficult if you try and shortcut the process. Okay, that's where bad things happen. So what we're going to do is we're going to go to the back, and I've got a tennis ball cannon. And we're going to shoot a tennis ball out one end, okay? And this thing is on a cart, okay? So I'm going to light it, boom. Tennis ball is going to go flying out one end. So what does the cannon have to do? Mr. Gilchrist.
What do you mean?
So if the tennis ball goes this way, what does the cannon have to do?
It has to push the tennis ball out.
Yes. Which direction is the cannon going to go after the explosion?
Opposite direction of the tennis ball.
Okay. Why? Why could the cannon not go in the same direction as the tennis ball after the explosion? Can I offer you a suggestion?
I'd like
Okay. Phone a friend, so to speak. Okay. So, before I light this thing on fire, what's the momentum of the tennis ball?
Zero.
Zero. Why?
no velocity.
No velocity. What's the momentum of the cannon?
Zero.
Zero. It's at rest, right? So, when you work these problems, you have to establish what's in the system. Typically, it's two things. It might be three. It might be four. Okay? It doesn't make any difference. But they all start the same way. So basically, what you're going to do is say, okay, the momentum of the cannon plus the momentum of the tennis ball has to equal the new momentum of the cannon plus the new momentum of the tennis ball. Okay? That's it. Because you always talk about the sums of momentums. Okay? That's what we're talking about. Just like the sum of masses in a reaction, we're going to talk about the sum of momentums. So don't shortcut this process. Okay? Figure out what you have. Okay, I got a cannonball, I got a tennis ball. When I add those two together over here, that has to equal the same thing over here. Start with that. Okay? Don't make it difficult. It's not a big deal. Now, over here, what does this side over here equal?
Zero.
Zero. Okay? Side is zero. Now, it doesn't have to be zero. It might be 100. It might be 3,000. It might be negative 200. Okay? In this situation, it happens to be zero because everything is at rest. Okay? So don't think, oh, every initial momentum is zero. No, it's not. No, no. Okay. So, Mr. Gilchrist, what's the only way these two momentums could add up to equal to zero?
They're opposite.
They're opposites. Okay? Same magnitude, opposite values, right? So the cannon is going to have a relatively large mass, and the tennis ball is going to have a relatively small mass, right? So could both of these velocities be positive, Mr. Gilchrist?
No,
Why?
because they have to add up to zero.
Bingo. So the only way that can happen is if one's going to have a positive value and the other one's going to have a
Negative.
negative value. So let's say that we're going to make the tennis ball be positive value. Okay? So it's going to have a pretty large positive velocity. So the only way that this can happen then is if the cannon has a smaller negative velocity. Right? So here's the deal. If I light that thing and both the cannon and the tennis ball go in the same direction, I violated the law of conservation of momentum. Because I would have two positive values which couldn't add up to equal to zero. Or I'd have two negative values, which would be even weirder, is that I shoot this off and both the cannon and the tennis ball go in the opposite direction, which would be really weird. Okay? Got the idea? So, let's see if it works. Get a nice vapor of that going. Okay? And we'll load up our projectile.
Are those just like tin cans?
Yep.
Homemade?
Yeah, I just took it and gas welded it together. Okay? And hopefully nobody walks in the door, especially Mr. Potts. Okay? What?
You match your cannon.
Huh?
You match your
I
cannon.
do. I wish I had that plan. Okay. Now, if you are sensitive to loud noises, you might want to cover up your ears if it goes like it should.
Where is it firing? Like which direction? That way.
Which way do you fire?
I
It's
didn't know
gonna
if it was
be
firing.
firing right to you, Kendra. Watch
I didn't know
out.
if
No,
it was
that's a legitimate question. No, it's going to go that way.
Just wanted to know.
Yeah, it's a good question.
Okay, thank you.
Okay? That's never a good sign.
Have you considered investing?
Use some
in one of those
force.
other
We don't know where this is gonna go.
Hopefully I do. Okay, here we go. 3, 2, 1. I told you it was going to be loud.
To cover your ears if you're sensitive. It was like a little, and this was not that.
Okay, this is a physics
Okay,
lab.
I know.
Can we do that again? Can we do it again? I wasn't expecting that. My mind was not prepared enough for what just happened.
Okay, let me I gotta re-oxygenate the can.
That's
'cause I
alright,
used
someone
to-
stand over there and catch it.
No, it's just like 100 miles an hour.
That's just a fastball from his ball.
Yes.
Well, I said it was gonna be
No,
loud.
but I just
You want
didn't.
me to go get the tennis ball?
Oh, we got it.
I was expecting just a little push, not like a very.
A little push.
I was expecting a push.
That was so loud.
Have you ever like determined how far it'll go?
Oh, we're giving this one.
Not really.
She wants to take it out to the hallway and fire. But then I
No.
But then I told
No, that would flip people out. They said no.
And then I told her that she'd probably break the fish tank.
Oh my god, do you know how bad that would be?
You know how,
What?
how bad would it be if somebody like walked in the door when you did this? Like
Bad, because one
perfect
time I
timing
did
and
this
it
and we opened up the door and shot the lockers across and we dented the lockers. Yeah. So,
No, honestly, just open the door.
well, I didn't wait, at the time I just built it, we didn't know how fast it was going. We said, hey, let's open the door and shoot the lockers and dented it. So, okay. Now, assuming that I got enough oxygen back into the system, we'll try this again. Okay. All right,
Let's go soon.
here we go. 3, 2, 1. Ah, hold on. Well, that's just it. You use up all the oxygen, and then if you don't get enough back, then yeah.
I was ready.
Mine's so
If this doesn't work, we just might have to let it sit and try it again.
So it's moved like the cup like
complained about the noise today.
I really don't care.
Oh my god.
I didn't do anything. He's back.
He's turning on him.
You didn't do anything. That mask just fell on its own.
Imagine if that whole thing would have fell.
No, I knew what I was doing.
Okay.
Oh, heard that one before.
You think I can?
Okay.
Oh, yeah, hold on.
Slammer.
What do you think?
Okay, yeah, you do that so I can see everything in slow-mo. I've done my ears.
Can't you put it in slow-mo like after?
Okay, here we go. 3, 2, 1, hopefully.
I did not follow it well enough.
Okay.
I didn't follow it.
Yeah, good luck. Yeah, try.
Like shook the entire
Oh, the
camera.
light's gonna slow down.
Did you get it going that
It's
way?
literally too fast.
Oh my god.
I got it!
Okay,
What if it speeds up on
But is this terrible? Why don't you do it like trying to hit a rock?
so the other thing that happens with momentum problems is that we always work like in an idealized situation of pretty much lack of friction. Because if you throw friction in, momentum is still conserved, but then you have to like take the momentum of the earth into account, and it's just awkward. So a lot of times when you look at momentum problems, they're going to be set like an ice rink, okay? Because there's a minimum amount of friction. Or you have an idealized situation like the cannon where it's on wheels. So unless you're explicitly told to worry about friction, don't worry about friction, okay? All we're looking at is what is happening with the momentum particles. So here's the setup. The other thing you see a lot of momentum problems, it tends to involve sports like hockey, like some problems involve like a hockey puck hitting a goalie or something like that because it's a frictionless surface, that type of thing. So in this situation, we're going to involve bullets and a block of wood. So with this one, you got a bullet coming in, mass of 10 grams, it's going to hit this block of wood. Now, when it hits the block of wood, there's 3 things that could happen. What's one of them?
Stops.
The wood, like,
Stops where?
go forward.
Somewhere.
Intonatio ad quitum.
Yeah,
Stop, force, and watch.
Yeah, okay? So perhaps it stops in the block of wood itself.
Yeah.
Okay, let's go with this option. So that's what's going to happen in this. The bullet's going to hit, the block is in effect going to catch it. So it would be like Hunter throwing like a big medicine ball at me, and I catch it, and then we move off together. Okay, it's kind of a California thing. Oh, let's move off together. Okay, so this is the California option. Now, what's another option that could happen?
Pierces.
Well, this is no.
All the way through.
It goes all the way through. So this is what's happening, like in the pictures up here where you have bullet hitting a banana, an apple, card, whatever, and going through. What's the third option?
It doesn't get to the block.
That's kind of the equivalent to it misses the block.
Hit the block and then push the block? That thing?
Yeah, but so then the bullet would like bounce off, okay, like it would ricochet.
So.
So basically, it can ricochet, it can stop within the block, or it can pass through the block. All 3 have the same idea, but yet are treated differently. So in this situation, we're going to assume that the bullet hits the block, and then afterwards, the block and the bullet are moving together at 3 meters per second. Okay? Because it's really, really tough to measure the velocity of a high-speed bullet. So if you look at that one, with that cannonball or tennis ball that we just fired, that was about 100 miles an hour. So imagine trying to precisely time that. That's at 100. You get a high-speed bullet, that might be, 600-700 miles an hour. So trying to sit there with the stopwatch going, fire it, Bubba, start, stop, got it. Okay? Yes. All right, so.
Isn't he the one with the barrel in?
Bubbles everywhere. You cannot teach physics without having bubbles. And my goal at some point in my life is to have a kid whose
Name
nickname
Bubba.
is Bubba in my class. Bubba, that's me. Okay.
Have you ever called a kid Bubba, like nicknamed him
Do you
Bubba?
have Bubba Soft in your class?
No.
Bubba was, there's no way he was that smart.
Now, his older sister I did.
Oh yeah, she was.
Yeah, Casey.
I just made that up. I literally have no clue.
Okay.
She's smart about it.
All right.
Dang,
So-
she's about as good.
Here we go. So all of these problems start the same way. Don't shortcut the process. So in this case, I'm going to have the momentum of the bullet plus the momentum of the block is going to equal the new momentum of the bullet plus the new momentum of the block. Okay? Boom. If there's 3 things involved, put 3 things. Don't shortcut this process. Now, sometimes Some of these will go to zero. Not all the time, but sometimes they will. So in this situation, what's the initial momentum of the block? Zero. It's at rest, okay? It's not moving towards the bullet, it's not moving away from the bullet, it's just there. So this is zero, okay? Now, how can I what do I have to know to determine the initial momentum of the bullet? Two things, velocity and the mass. So this is going to be the mass of the bullet, velocity of the bullet. Now, this is going to be the mass of the bullet times the new velocity of the bullet plus the mass of the block, the new velocity of the block. Now,
Alright.
huh? Good?
No, I'm not good.
Mass of the
I'm not good. We'll get it.
B.
Now, here's the kicker. What's the final velocity of the bullet?
Zero.
Zero. Everybody cool with that answer?
Yeah.
Bullets zero.
Wait, no, I'm not.
Whoa.
I'm not cool with that.
They were both moving.
They are, so I'm not.
They are.
Why did you say that?
I didn't, I just said it's.
You said right?
No, that's him being condescending.
No,
Condescending and tricky.
think about this, okay?
Condescending and tricky.
So, I might have set the evil trap that some of you fell into, and it's like, okay, so here's the deal. The bullet's inside the block, right?
Yeah.
The bullet's inside the block. So, it'd be like me sitting here and me catching medicine ball, right? We're both going to be moving off together.
Can we cancel out the mass of the bullet?
Why?
Because it's adding.
Hold on. Because if you cancel...
Just kidding.
Yeah, no. Okay. So, here's what's important in a problem like this. These velocities are the same because it's embedded in the block. So if these velocities are the same, what can I do? Rhymes with actor out,
Factor out.
factor out. So I can write this as the mass of the bullet plus the mass of the block times some v prime. Okay? This is a cool thing to do, but you can only do this if they're moving off together. Okay? So if this is a communal thing, where they're moving off together, you can do this. If the bullet hits and bounces back, you can't do this. If the bullet passes through, you can't do this. But if they stick, or even if it's like two train cars, if two train cars are sitting and they collide and they move off together, you can do this. So you can do this, but be very, 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 very careful about when you do this step. Now I got the mass of the bullet, velocity of the bullet. So it's the only thing at this point I don't know.
Velocity
Yeah,
of the
V.
block.
Bullet, right? Because I know the mass of the bullet, I know V prime, I know the masses of everything involved. So to get this, I'm just going to divide by the mass of the
BU.
bullet. Right? Now, I'm going to point this out. There's a 99.99% chance that this won't happen, but I have to point this out because there's a slight chance that it will. Can I just cancel out the masses of the bullets?
No,
Nah.
No. Why?
they're added together.
Yeah, they're added together up here, so I can't do that. Okay? Can't do that. Okay. Now, before we actually calculate this value, is this velocity going to be bigger or smaller than 3 meters per second? Brooklyn. Bigger or smaller? Bigger. Number one, it's a bullet. Okay? Probably going to be going pretty fast. But here's the bigger kicker about why your answer is right. These momentums have to be the same. Okay? That's the big picture. The momentums have to be the same. So this combined has a pretty big value of mass. And it's moving pretty slow. So that means the bullet over here, which is going to have the same momentum, has to have its mass is really, really small, so it has to be going
Really fast.
really, really fast. Okay? Is there a chance that this velocity, when I find it, could be a negative value? Howie, is there a chance that this velocity, when I find it, could be a negative value? No. In this situation, it can't be. Why?
Because the masses are all going to be positive, and we know that the v is a positive number. And then if you do like a time graph, it's not, they don't change directions.
Beautiful answer. Fantastic. Beautiful. Okay? Now, physically, why can't the velocity be a negative value? What direction would it be going?
Going the opposite direction.
It'd be going the opposite direction. Because if the bullet's go this way and that's positive, okay, yeah, the world is round. If you put it into orbit, okay, it might come back around and hit it, then block's going to go that way. So, physically, it just doesn't make sense to end up with a negative value. Now, that doesn't mean that, oh, no velocities are ever negative. In this situation, it just means it doesn't make any sense for it to be negative. You can have negative values, just not in this case. All right. So I got 10 grams. Need to change that to kilograms. Divide by 1,000, multiply by 1,000. Multiply by 1,000. So this is going to be a 10,000 kilogram bullet. It's going to be 10,000 of these.
No.
That is a big honking bullet.
Yeah, that's a rocket.
Oh, yeah.
Could you imagine if we just shot those out and they didn't explode and just...
Oh, yeah, it's a kinetic energy situation. That's kind of what we're going So let's divide by 1,000 and get 0.010 kilograms, right?
Yeah.
Or do I need another zero?
No, that's
No,
right.
you're good.
Okay, yep.
You're
Right,
okay, sir.
so we're here, 1, 2, 3.
Significant.
Okay.
300 meters.
So, somebody take 1 kilogram.
Meters a second, sir.
What is it?
303 meters a second.
Okay, so if you do the math, you get 303
Yeah, I'll go
meters per second.
Pretty fast.
Okay? Not quite the speed of sound, but pretty close. Okay?
Wait, what?
All right? Good with this. So all I did is I took the mass of the bullet, added it to that, multiplied that by 3, divided back by the mass of the bullet, got
I want
303.
to shoot bullets in space.
Huh?
I want to shoot bullets in space.
Would it be just super slow?
Why would it be super slow?
Because everything in space is slow motion.
Yeah. Don't you ever notice that?
You didn't know that?
My bad.
You taught us this theory.
Yeah.
Slow motion.
No. I
Everything's
taught you that if you're on the moon, things fall slower because it doesn't.
No, you said in deep space
I
everything's
never
slow.
said, oh no.
So the bullet would just be fast still?
It would just go on forever. That'd be
So now you're contradicting yourself.
Okay, so if you're on the moon, how fast is that bullet gonna go?
It's because what's determining the speed of that bullet is from the gun that it's firing. That's an internal system. If anything, it's going to go faster because there's no air resistance to impede it once it leaves the gun.
I thought it was gonna be like the Matrix.
The Matrix?
So if somebody shot you in space, you're actually not going to get shot.
Okay.
Because there's no friction. There's no friction on the moon.
Now, here's what I want to look at. I want to look at a velocity time graph for both the block and the bullet. So here's the question.
Who cares?
Is the bullet, when it hits the block, going to accelerate?
You're so dumb.
Yep.
Yeah.
Yes, it's going to decelerate. Good one, Grant.
Funny.
Well,
No.
Heathen,
Does that
non-believer. Okay, so let's talk about the bullet. Where's the bullet's velocity time graph going to start?
God,
super duper high.
About 303,
That's
Yeah.
awesome.
Super duper high.
okay? And that's going to drop to what?
3.
3.
Good answer.
Or take a while, or
At
pretty
first
slow?
it's gonna be like, gee, and then it's going to
Okay, let's just look at it. Right,
It's gonna be
starting at
constant
point
for
of
a little
impact.
bit.
Oh, point of impact, yeah. It's
Okay.
Constant to the point of
It
impact.
is really good for impact.
Right?
Is the point of impact up
So
there?
it's gonna end up at 3 meters per second, right?
Yep. And then
So
you
this
said
is the
no
bullet.
for friction.
So what's the block gonna do?
It's just gonna be a 0 and then all of a sudden it's gonna be, alright.
Ellie? What's it gonna do? What's the block velocity time graph gonna do?
I know it smells really good. Did you spit on lotion?
Right behind.
Start at 0 to 3.
Yeah, so it's gonna, the block is gonna start at 0,
I thought you were gonna-
and it's gonna go to 3 meters per second. Okay, so this is while the bullet is slowing down and the block is speeding up. Now, assuming that there's no friction, so after this point in time, what is this line gonna do? Yeah, then it's just gonna be a horizontal line like this at 3 meters per second. So, here's the question. Do I have enough information to calculate the change in momentum of the bullet? Do I know the mass of the bullet?
Yes.
Do I know the initial velocity of the bullet? Do I know the final velocity of the bullet? Yep. Check me if I'm wrong, but I think I can get the change in momentum from those quantities.
Nope, you're good.
I'm good?
You're right.
Okay?
You're right.
Man card. Come on.
I don't care. I like smelling things. Good, good. I like girl smells, honestly. Like, girls smell so
Okay, stop.
pretty. You ever thought about that? How, like, perfume and cologne work differently? Like, we smell not good. It's kind of more of like a. Like, it's a more alcohol-y or like musk scent thing. They smell so pretty. Girls smell so flowery.
Just stop.
Oh, okay. Girls are
Just stop.
This is the point in like our TV show thing where I wish we could have like little individual segments.
See, Hunter calls it a
Now-
TV show too.
This is a TV show.
And like in a reality show where like after a segment like we get our like own little like
They're called segments now.
God, I can't believe Bert just said
We have like a confession room. It goes
And when
in
he
and
said
it's
that, I could not believe
They go back there
They
and
go
they're
back
like,
there, they take the camera.
And then Lexi put on that lotion.
Maybe at
and
the
I
end of
just
the
lost my
class,
stuff.
you know, everybody gets like 30
like half of the
seconds.
videos of them just like playing with the balls back there and they're just like, ah!
No.
that
Or
was
Reese like
I feel like we should
Yeah.
do one edition like that.
Okay. So, what's the final velocity of the bullet?
0.
No!
3.
3! What's the initial
It's a relative
velocity?
scale. 300 degrees.
Okay?
Good.
So somebody take 0.01 times 3 minus 303.
Oh, wow.
Where's the 3 coming?
Hey, I'll do it guys, don't worry about it.
Oh, final.
If someone says the answer, I'm gonna do it. It's -3.
I could have done that in my head if you would have told me the
Yeah, I
answer.
could have too.
If you would have told me the answer.
So, this is
Why
the
not?
change in momentum of the bullet. Did the block change momentum?
Yes.
Yeah.
Yes. Can we find that? I think so.
Do you want us
Yeah,
to
you
find
just
the whole
put
system?
0 plus 3.
No, this is just the block.
the
Okay.
momentum theory.
So that's going to be 1 kilogram. Final velocity of the block, 3. Started at. So I get
John Cena outfit all day. And it was nothing.
positive 3 seconds.
And then if you add those together, it gets 0 because of the relative scale of momentum.
Oh, and then they cancel out because they're equal.
Oh!
I literally just looked at the board and I was like this.
Okay.
Huh?
Is it coincidence that these are the same but opposite? No.
Oh, wait a second.
No. Because look, did the bullet lose momentum? Yes. Where did it go?
Into the block.
Into the block. Momentum has to be conserved. So whatever momentum is lost by the bullet has to be gained by the block. Okay. Now, let's say that this took, just to make the math easy, 0.1 seconds. Okay? 0.1 seconds. That's the time from the point of impact until it started to move off at a constant velocity. So if I know this 0.1 seconds, can I find the force acting on the bullet?
Yeah.
Yes, because change in momentum equals
Force times
force
time.
times time. Okay? So change in momentum equals force times time. So if I divide by time, right, I get my force. So that was -3 Newton seconds.
I am so hype about this.
So seconds cancel out, I get a
30.
force of
Negative 30.
-30 newtons. Now, this is for the bullet. So for the block, guess what?
You get 30 newtons.
Oh!
I love physics more than anything.
So,
Except for girl perfume.
Girl perfume.
It's the prettiest smell.
I want to feel like perfume.
no, don't.
This is actually the embodiment of what like I think that just a beautiful
A perfect
woman
girl.
smells like. Like if you showed me a woman, you know, just
This is the smell
Just
that you would picture her with.
frolicking through the meadows, I would picture she smelled like this. And it honestly makes me smile.
I just, rare that I am at a loss for words.
If I found that girl,
I have no words.
I would treat her so well.
I have no words.
I would
Okay.
honestly
Anyway,
every
all
day.
right, we're good. I don't
Every
care.
day.
We're good. I don't care.
I kind of want to smell it now.
No,
Is it really that good of a smell?
Yeah, that's pretty good. It smells like,
Honestly,
you
that's
know,
it's better fresh.
fresh out of the shower smell, kind of.
What are you worth? What is your body? That's worth
Not me. Like,
Give that a smell.
That's all these
Okay.
girls. That's all these girls getting out of the shower. What? Because he was like, that's not fresh out of the shower.
okay. So, basically, you prove,
Honestly, it might be.
you prove Newton's third law by the conservation of momentum. So these forces are equal and opposite because when the bullet is slowing down, that's exerting a force on the block. The block is speeding up, it's exerting an equal and opposite force on the bullet. The changes in momentum are equal and opposite. The forces are equal and opposite. Voila, we have Newton's third law. Okay? Got it? Good? Great. All right, now, the changes in momentum are equal and opposite. The forces are equal and opposite. Are the accelerations going to be equal and opposite?
No,
Why not, Kendra?
because you have to have the acceleration to compensate for the mass.
Okay? So,
If it has a really...
it adds to it if you do this.
I'm
Okay?
sorry, I just needed a little like extra.
Okay. So, which one of these, the bullet or the block, is going to have the larger acceleration?
The bullet.
The bullet. Because look, if you look at F equals ma, right? The same force. So the bullet is going to have a small mass, so it's going to have a large acceleration. The block has a large mass, so it's going to have a small acceleration. Now, you can also look at that on a velocity time graph. So even if I know that this is 0.10 seconds, I can find the slope of this line. I take 3 minus 303 divided by 0.1, I get this acceleration. I take 0 minus 3, divide that by 0.1, I get that acceleration. Or you can just visually look at it and go, wow, that line's really, really steep. That's going to be a big negative acceleration. This line is positive, pretty shallow. That's going to be a much smaller acceleration. So you can just even look at the velocity time graph and say, wow, okay, the accelerations aren't the same. So here's the deal. When you have any type of collision, changes in momentum, equal and opposite. Forces are equal and opposite. Accelerations are not. Unless there is one situation where even your accelerations will be equal and opposite.
If they have the same mass.
If they have the same mass, okay? If there's any difference in masses, your accelerations will not be equal and opposite, okay? But here's always, always, always true. Changes in momentum, force, always equal and opposite. So when I give you this question on the test, don't overthink it. As soon as you see forces or changes in momentum, don't overthink this thing. They are always, this is a law, they are always equal and opposite. Okay? And don't say, well, oh, the negative value is less than the positive value because this is a reference to 0. No, this isn't a math class. Okay? Right? This isn't a math class. -3, +3, same thing. Only difference is the magnitude. One's negative, one's positive. Don't flip out. Okay. Now, let's look at this. So, I've got this set up. And these are two different polymers of marbles. So, one, when it bounces, okay, it just basically hits and stops. Okay? The other one, when it hits, is,
It's like a bouncy ball.
yeah, pretty bouncy. Okay? So, I'm going to take this first one, lift it up to about yay, and drop it. Okay? Hits, basically stops. Then we'll do the same thing with this one. Hold it up to about yay, drop it.
Ooh.
So here's the question.
It bounces back.
You're
so it's
just-
gotta get a bigger.
Trying to trick us now.
This is trickery.
Why does the nails?
I've
bend?
never
you a
seen
wizard?
something like that.
So here's the deal.
One had more force. How's that?
Oh, one had more force.
How's that possible?
I don't know. So here's the deal.
Held it up higher.
Whoa.
Here's the deal. So let's say, what happened to my tennis ball? Tennis ball.
You shot it.
I know I shot it.
You shot it
Where did
twice,
it
sir.
shot twice, actually.
I don't know where it went.
Everyone, let's stop class.
Hammett's got it.
Joseph, could you go back in that drawer that, keep going, keep going, keep going, keep going? Oh, or just,
Launch that sucker.
okay.
Wow.
All right. So visualize this, Mr. Taylor. Okay? I'm going to throw this to you. The first time, I just want you to catch it. Okay? Got it? Okay.
Are you an
Now,
athlete?
roll back.
One hand.
Star receiver.
Okay?
Receiver.
Now, this one, I want you to take your hand and I want you to treat it like a tennis racket. And I want you to hit it back to me,
Got?
like that. Okay?
Got
Can you
it.
please get
Got
this
it?
on film?
Okay? Now I just want you to catch it with that hand. Okay, ready? Now, what felt like it took more force? To hit it back or just catch it? Why?
Try to like move my arm.
Okay? But think about this. If you just caught it, what was the final velocity of the ball? 0. If you hit it back to me, did you still have to stop the ball? But then you had to,
Go again.
yes, which is going to take more force. Okay? So if you look at what happens with these, the one that hits and bounces undergoes a much greater change in momentum. So if you look at a velocity time graph, the one that bounces, okay, here's 0 meters per second, right? So the one that bounces, right, it's moving along, right, boom, hits the block, goes to 0, but then it has to change direction because it's going to bounce all the way back. So this is going to be a very, very big change in velocity. So that's going to create a big change in momentum. Big change in momentum requires a big force. Now, the one that just hits and stops, it's moving along, right? So if we draw that line, it's going to be moving along, it's going to hit, and it's basically just going to stop at 0. So the one that just hits and stops doesn't make it bounce as far because of the fact that it doesn't undergo such a large change in momentum.
So is the reason it has more force because of potential energy?
No, they both have the same potential energy.
Then what is going on? What is this?
This graph is what's going on.
I know,
So-
but one has more force acting on the block, obviously.
Yes,
'Cause
because it
bouncing
has to
back.
stop. That force has to be provided by the block.
The block is providing a bigger opposite because it's bouncing back so far.
Oh my god.
He's right.
Okay, listen.
It's
why?
just-
Like, why? Where is that extra force coming from?
The ball.
Okay,
Oh, dear.
basically, it's stored with, part of it is potential energy stored in the polymer and the structure of the ball
That's what I was
itself.
meaning, yeah.
that, okay, I thought you were talking about like a macroscopic view of energy. Yeah, because basically on an atomic level, you're storing
Yes,
it,
yes, yes.
and on an atomic level, you're storing that energy, it's rebounding and going back. Whereas the other one, it just basically hits and it disperses that energy out. Okay, I didn't realize you wanted an atomic view of it. Okay, good, stop that. So,
We're going to Cubby's house.
We're going to
Watch the
Cubby's.
Fall Classic.
okay,
What do your parents allow? We're talking.
no. All right, so when you look at question number 4, where you have 2 bullets of equal mass shot at a block of wood resting on ice, don't get hung up on the one that embeds it, going, oh, the mass becomes bigger. Okay, the change in mass is minuscule. Look at the bigger idea of it bouncing off, okay? When you're talking about question number 2, if only an external force can change the momentum of an object, think about trying to stop your car on a sheet of ice, okay? So you hit the brakes, but what do the brakes technically do? The brakes stop your tires, okay? That's an internal force. It takes friction, which is the external force, to actually make the car stop. When you get to question number 10, so let me lay this out. This is old school inclined plane stuff. So you've got a block sitting on an inclined plane. It's going to slide down a frictionless inclined plane. It's going to accelerate. Then at the bottom, there's another block. They're going to hit and they're going to move off together, kind of the California thing. They're going to move off together, but then it's going to come to a rest because now there's friction. So while it's on the inclined plane, there is no friction. It's going to hit the block at the bottom, they're going to move off together, and then there is friction. Okay? So that's the setup. When you get to question number 11, you have 3 astronauts floating out in space, Huey, Dewey, and Louie. Okay? So, by the way, Huey, Dewey, and Louie are?
Donald Duck's nephews.
Yes, Donald Duck's nephews. So,
How did you know that?
This is a quick thing
I
too.
watch a lot of Disney, man.
so here's the deal.
I had no clue.
So Huey and Dewey are going to push off of each other. So think of this as like the cannon and the cannonball. They're going to push off of each other. So they're going to be going in opposite directions. One of them's going to run into Louie. Louie's going to push the other one back like that. So what you want to do on number 11, lay out what's going to happen to all 3. Now, don't go macabre and weird on me at the end and going, oh, they're going to die a lonely death out in space. And Sam Harrison wrote an entire novel on this question, literally. Why no, but, I mean, it was just, I mean, literally. Yeah. So, this is not, and again, don't think, I don't want this long macabre,
Oh, this is gonna be a
Honestly,
good.
let's write it.
okay. Just look at the physics part of it. This isn't like Edgar Allan Poe physics.
Should do it.
It's just
I honestly
physics.
feel like I have a connection to Louie.
It's Huey.
I'm happy for you.
So they all are.
Anyway, I'm done. You're on your
Say
own.
life is just